inviting me to this summer school at this nice and interesting island, and for giving me the task of filling up 100 minutes at the start of the morning. Not only a challenge for myself, but I think also a challenge for the public. So, but let's go ahead. I hope that at least some nice pictures will sort of compensate for what is coming up in the coming 100 minutes. So what I was asked to talk about, or to review, is basically an introduction to the cosmic web. Now that's a vast subject, and actually I have two sets of slides, which doesn't even fill up that. The other one is sort of, sort of a reserve if I manage to finish everything after 50 minutes, and you will see that that's a joke. Then I can talk about the second part, which would be about flows in the cosmic web and about voids. But I certainly won't be able to get up there. So the concentration, the focus of my review will basically be the structure and the dynamics of the cosmic web. So what is the cosmic web? Let me first introduce to you the cosmic web by nothing more than a hypothetical distribution of mass coming out of a simulation showing the dark matter distribution in a lambda CDM universe. In this case, it is the so-called cosmogrid simulation. It's a simulation in a rather small box. But what I want to show you is a kind of a CT scan through the universe, as supposedly it has formed 13.8 billion years after the Big Bang. And what we are going to do is walk through a box and look at the structures that we see over here. And the simulation has a characteristic, very refined grid of structure, very characteristic of the cosmic web. And what I want you to take away with is, first of all, to see the kind of structures that you see, clearly anisotropic structures. Some of them are flattened, some of them are elongated filaments. That's one thing that is very obvious that you already see over there. The second very important point is that connectivity. These things are not scattered around randomly. They are connected in a particular way. They are organized in this box. They are connecting up. So what we see is that filaments are connected to high density nodes. And actually when you see, for example, elongated objects pursuing through the box as the CT scan goes, then of course you're not talking about a filament, an elongated object. Then you're talking about the flattened structure, a wall. And we will see that there are both walls and filaments. The next thing that you should take away with is that the blue structure is of course the overdense regions, the dark matter distribution. The black stuff is the voids. Now when you see here the first slide, it's not that obvious. But look when we pass through the box and you see that there are large underdense regions. They first are small, then they open up as the box is passing through these voids, then they close again. And you see that actually these underdense regions are the majority of the volume in our universe. Then the fourth point, very important point, is that this structure is not on one particular scale. It's not that you can say, well, on a megaparsec, there you sort of see all your cosmic web structure. Actually, when you look, you see that all this structure is to be found on a whole spectrum of scales. You have nodes and clumps, very small clumps, sort of galaxy-sized halos or even sub-galaxy-sized halos, up to very massive cluster-sized halos. But you also see the filaments. You see the elongated structures, some of them huge, like you see this one over here, other ones just small tendrils passing through the box. And it's a whole spectrum of them. It will be the same with the walls, but that's far harder to see, and we will see later on why that is. And interestingly, it's the same for the underdense regions, the voids. They also have a hierarchy of distributions. So, given this message, I hope that sort of you can follow the movie. Let me see. Oh, it worked a minute ago. Yeah, so there we pass. So you see, did it stop already? It should be there. So you see you're passing now through the box, and you clearly see the connections. You see, for example, here, a large void that started first small, and then expands, and then it becomes smaller again. Inside the void, you see a lot of similar things, much smaller scales, with boundaries that are filamentary-like. See here that, for example, this thing here is pursuing over a whole range of scans. So that's not an elongated filament, that's a wall. And you see the way they are connected. You see the filaments are sticking in these overdense regions. It's clearly a network. And of course there are a lot of interesting questions like how many of these hairs are sticking out, or this kind of stuff. So the movie in itself shows the intricate structure of the cosmic web. And it's clear that a pattern like this should contain a lot of information about a range of subjects, about the cosmic structure formation process, hopefully about cosmology itself. Does it carry an imprint of the overall cosmology? Of course, when you are an astronomer, you would be interested not in the dark matter per se, but in the objects that are living in there, like the galaxies. Are the galaxy properties related to the underlying structure? Those are all kinds of very interesting questions that we would like to ask, and that makes the cosmic web a very interesting subject to study. So we will try to do that in the coming 100 minutes. Now, just to give you another three-dimensional impression, here on the background you have a rendering of the filamentary structure in the cosmic web. This was made by one of my students, former students, Johan Hidding. I must actually say that a lot of the work that I will be presenting was carried out by three of my students, Johan Hidding, Marius Cotin, who should have been here, but I haven't seen him yet, and Job Veldbrugge. Is he here? No, not yet. Maybe he's playing the role of dark matter, I don't know. And then there is Job Veldbrugge, with whom I'm working at the moment. Now what you see over here, actually, is an analysis of this dark matter distribution that you saw in the previous box by a particular method of classifying and identifying this cosmic web-like structure. Something that I won't touch upon in detail today is, of course, what we see is this structure is very complex. An analysis in terms of spherical filters or something like that is not going to work. This is a complex structure with all kinds of shapes. So you cannot a priori say, I'm going to look only for shapes that look like this, because you see the huge variety. You also cannot look intrinsically at a certain scale. Say, I'm going to look for only objects of 5 megaparsecs, because you're missing a large part of the story. So you have to come up with new techniques. And actually over the past 10 to 15 years, a range of techniques have seen the light. Actually, there was a recent paper by Noam Liebeskind, myself, and a range of people here in the room. Paco was involved, comparing a range of these techniques, because they are all trying to describe the same thing, lift out certain objects, try to relate them. But of course, they have various backgrounds and various principles. And the question was, in how far are they looking at the same structure? Now this particular technique is our own. It's called Nexus Multiscale Morphology Filter. And as you see, it very nicely lifts out the three-dimensional filamentary structure. You see how very nice. You see the huge filament over here, and you see the little tendrils sticking out. When you show this to your colleagues from the university hospital, like I did recently, they say, oh, this is the veins in your body, right? Or the arteries in your body. No coincidence, actually, the technique was actually emanating from medical research. It is a technique that was devised for medical specialists, actually. You know, when they make CT scans, they want to look for certain objects. But, you know, a medical doctor cannot spend 24 hours a day looking at pictures. So you want to have some automatic procedure selecting these photos and say, you may have a look over here, there is a lump over there, might be suspicious, right? That's what they are interested in. So we actually use the same technique, but for the cosmic web. And you see how very nice the cosmic web is actually doing exactly the same thing as arteries or veins in your body and a lot of other things. So actually there's also a cross-disciplinary talk in developing techniques that are able to highlight the structure. Now, this is a kind of thing, I presume that these slides are going to be put on the website or something like that, so you can read this. It's a quote that I often use because very many colleagues, astronomy colleagues, always ask me, what's the use of this cosmic web, right? Like, why would you want to do this? And then you have to explain, well, you can do cosmology or you can look at galaxy evolution. I myself actually are interested also in the intrinsic beauty of the cosmic web. It's an intricate, very nice structure, and it's the largest structure that we have in the universe. So here I always use this quote that was written down by Balbus and Holy, and it was in a completely different context. It concerned magnetohydrodynamics. But it's the same thing. They point out that when you see very complex macroscopic patterns, it's usually the manifestation of a range of underlying physical forces. And understanding the complex pattern is actually a way into understanding the underlying physics. Right? So that's usually my justification of the story. Now, I won't have the time for a very elaborate introduction on the observational side to the story, but at least, of course, I should introduce some of the structures that we will be talking about and sort of try to investigate the underlying characteristics and properties. Here is a rendering of the cosmic web. Again, you would think this is a theoretical picture. This is the analysis of the underlying dark matter web in some simulation. It's not. This is the real world. Actually, for those of you who are astronomers, this is, and you know about the Piscis-Perseus chain, this is the one. This is actually, this was made by Johan Hidding on the basis of an Adhesion reconstruction of the local web on the basis of the chi-chain reconstructions of the initial conditions by Paco and Stephen Hess. And on the basis of that, I will describe it later on, with a particular dynamical model, you can forward the evolution of the mass distribution in our local universe and try to look at the resulting structure. Now, because we were particularly interested in the cosmic web, the so-called adhesion formalism, which I will describe in some extent later on, is perfectly suited. It doesn't really describe all the intricacies of the dark matter distribution down on all small scales, but on the scales that matter for the cosmic web, it does find actually the structure. So you see these huge arteries like this, and they are real. Now you also see the small tendrils over here, and later on we will argue they are part of this particular realization. But if you take another realization, it might vary a little bit. They're not always on the same location because the data that we have are not everything confining on the very small scale. But at least you get an impression of what structure in the local universe, when you would see the dark matter web, looks like. And it looks, yeah, very intricate, very nice. Going back in time, what would be the first instances in which we start to recognize the cosmic web. Usually, I would say the most marked point is the 1986 publication by Valérie de Lapparent, Margaret Geller, and John Huckra, Slice of the Universe. This was the first time that we saw a sort of bubbly universe of filaments and walls and etc. in the small CFA survey. However, when you really look back in time, very shortly before that, a couple of years before that, Jim Peebles published this map of the projected distribution of 1 million galaxies on the sky. And in the Shane-Wirtenen counts, this was based on meticulous counting in the early 60s by Shane and Wirtenen. For years and years and years, these guys were counting galaxies on photographic plates, and they put this down in 6 volumes. Can you imagine these days, of books? And this actually Jim Peebles gave to his daughters, because in the holiday, that's what he told me, in the school holidays he had to give them something to do. They were at elementary school at that time. So he gave them these books and he gave them a painting set. Imagine plotting programs, right? A painting set, a painting brush with white paint, and he gave them the task to put, you know, on each little grid point a little dot if there were galaxies. And this came out. It's a beautiful map, 1 million galaxies. And when you look at it, you really see, at hindsight, this is the cosmic web staring at you, right? Not that it was realized at this time, but you see, you know, large concentrations like here, but you clearly have the impression of filamentary structures. So I would say this is perhaps the first time that we really get an impression of the existence of this thing. Look at the contrast of this. This is a reconstruction that was made by Paco here on the basis of the 2-mass redshift survey based on his Bayesian inference machinery, very sophisticated. And then you get this beautiful map of the local cosmic web around you. We are sitting here in the midst of a dark matter spider web, right? So this is, in contrast to this is the advance of decades of work and you know, sophisticated new techniques. I guess you will be talking about this during the conference, to some extent. Now, what are some of the overall properties of the cosmic web? Now, one thing that you might conclude is that overall you have these underdense regions. They are the low density regions. The nodes, the cluster nodes, they are the very highest density regions. Then the filaments, they are somewhat medium density, and the walls are somewhat in between. That's what you would say. And actually there are some methods that use that density criteria. Now, if you look at it, it seems to be a bit more complex than this. If you look here, you see what the various morphologies, and here we distinguish 4 morphologies: voids, walls, filaments, and cluster nodes, right? How much do they occupy in terms of mass? How much do they represent? And how much in terms of volume? That's the first question. Now here you see in mass fraction, actually 50% of the mass in the universe finds itself in filaments. This is based on our Nexus algorithm, but overall most algorithms for classification of the cosmic web are finding results in the same vein. They are approximately, you know, there can be a variation of a few percent, 5%, but that's sort of what you get. That is most of the impression that you get when you look at these simulations is, or at the redshift surveys, is that most of the stuff, most prominent, are the filaments. That's confirmed. Most of the stuff seems to be there. Look that 11% finds itself in the cluster nodes, in the high-density compact nodes. even though in volume they are almost negligible. Because if you look to the right, here you see the volume fraction, and you see very minor part of the volume is actually filled with the nodes, because they're just the points that connect all these structures. But they do represent more than 10% of the mass in the universe. That's why they are having densities over 1,000. In terms of volume, of course, most of the stuff is underdense. It has a density less than 20% of the mean density of the universe. That's a characteristic mass or density for voids. And you see most of it is in voids. That confirms what you see, right? There is clearly the underdense regions dominate your volume, right? And then the walls, well, they're sort of in between. In terms of mass, they represent 10 to 4%. In terms of volume, around 18%. Now, when you distinguish this and look then at the density distribution, you see something equally interesting. If this is the density range of the nodes, and you see, it makes sense, right? I mean, here you have the real big guys with an overdensity of around 1,000 to 10,000. Those are the cluster nodes, right? You have minor ones like groups and things like that. They are more in this regime. And you even have some small nodes that are not very dense, but they are nodes in the cosmic web. This line here, that's the voids, and you see that the voids are indeed, you know, 100th, 1/10th. That's where most of the underdense stuff is. You can actually forward a dynamical argument why 20% is a characteristic density for voids, and you see it's in this range. And that's where most of the stuff is. But it goes all the way up to almost the mean density of the universe. We have lakes that are sort of almost the mean density. And actually, in the mountains of the landscape of the universe, there are even some lakes that are in the mountains. And they are the overdense voids, almost, right? So they are little lakes over there. But the most interesting population is the filaments. Their range is vast. They go from less than 1/10 up to almost 1,000. 1,000, those are the guys that are connecting up to these high-density nodes. They're sticking out like the extensions of this. Right? They have themselves huge densities. But you saw that in the voids, remember this CT scan that I showed you, that you have very small tendrils who are very tenuous. They have very, very tenuous densities. And actually, we found that also if you look at the Sloan survey, you can even see them. We looked systematically in our so-called void galaxy survey, where we systematically looked for a population of void galaxies, which nearly all turned out to be very small, minor galaxies, not just dwarfs, but slightly more blobs. They were more like that. Some of them were found to lie on a line which turned out to be a filamentary extension, sticking into a void, but with very low density. So the filaments, you can certainly not characterize by a density criterion alone. You have to look at at other measures. Okay, I think I can skip this because I already told you the 4 main characteristics of the cosmic web. It's the anisotropic structure, the filaments, the walls, the multiscale nature, the hierarchical distribution, the dichotomy between overdense and underdense, with the underdense regions taking care of more than 75% of the volume. That while the initial Gaussian conditions said that we started from 50-50, right? So clearly the nonlinear evolution has led to a shift away from this, clearly non-Gaussian behavior over here. And then something very interesting is the complex structural connectivity of all of these things in the cosmic web. Okay, I think I discussed this already, this Piscis-Perseus supercluster. this is the multi-scale nature of the cosmic web based on a adhesion model, and you see the nice thing about the adhesion is that you can really look at the evolution of the structure themselves, of hierarchical structure, and you see that as you zoom in over a vast range of scales, you start to recognize this cosmic web-like structure. But you also see it in simulations. For example, there is this picture by Volker Springer of the Millennium simulation, and you clearly see that on a whole range of scales, you see this cosmic web-like structure. Voids. So the underdense voids in the universe, now how prominent are they? Here you see a rendering coming from the same reconstruction of the local universe by adhesion. So this is based on the 2-mass survey. This is looking edge-on of the supergalactic plane. So here we clearly see the supergalactic plane. This is where we are. This is where the Virgo cluster is. This is towards Coma. If you look the perpendicular one also on the edge-on, you see that you more go towards the great attractor, Norma, and you see all the voids over here. Local void, Aquarius void, sculptor void, and all this kind of structure. So voids are really an important part of the cosmic web. Connectivity, so how does it all connect together? So again, this is a movie, this is based on a nexus analysis of this simulation. What you see here as green-bluish is the filaments. What you see as orange-red is the walls. And here they are already tagged, the particles are tagged, but of course it's nicer to see how they connect together. So this is the filaments, and this is the walls together with the filaments. And to get the three-dimensional view, I should play Unity. And I hope it goes like this. So here you get a sort of an impression of the filamentary network. And you clearly see it's a network that connects all the way through the universe. It's not, disconnected filaments. They are all connected, and they have a variety of scales. And you see that when you look here at this second part, you see the filaments, and they are clearly also forming the boundaries of sheets, of membranes that we recognize as walls. Now, later on, we will see that these walls are actually not having only a lower density, but their surface density is incredibly low. That's the reason why in observational circumstances it will be very hard to see these walls, but they certainly are an intrinsic, integral part of the cosmic web, right? So that's sort of the main characteristics. So why physically? What would you have to answer when people ask you, what's the use of looking at the cosmic web in a cosmological context? So, like I said, it's just nice, it's beautiful, blah, but in particular, when you look more down to Earth, the point is that the cosmic web is found exactly there where the universe is transiting from its original primordial linear mass distribution, the Gaussian distribution, to the fully nonlinear distribution. It is actually forming exactly there where it goes mildly nonlinear and starts to form the first real structures in the universe. So it's the first phase of real structure formation. That means it still has a memory of the initial conditions, given that you have come up with a good description of these first nonlinear circumstances. You can actually use it as a real probe potentially for cosmology, right? Then there are certain aspects of the cosmic web that are very sensitive to the underlying cosmology. We heard 2 days ago, we had a lot of talks also about dark energy and probes of dark energy. And of course, you have lensing and you have the supernovae. But it turns out that, for example, when you look at these underdense regions, the voids, they are incredibly sensitive to the underlying cosmology. Very sensitive to, for example, the dark energy. They're very sensitive to modifications of gravity, simply because they have a far lower density than average, so they're much more feeling the effects of things like dark energy or minor modifications of gravity. But on top of that, because of their low density, they keep on being very, very sensitive to the overall surrounding dark matter distribution. And because the growth of that surrounding dark matter distribution via the growth factor is very much dictated by the underlying cosmology, you see directly the imprint in, for example, the voids. And we actually tested that in a range of simulations with different dark energy prescriptions, going from quintessence to supergravity and those kind of things. And indeed, potentially you can look at void shapes and see what kind of underlying cosmology there is. The bad thing is, you would have to look back in time because it's the evolution of their shape that is influenced by the dark energy. So not only Z to 0, you would actually have to probe further on. Of course, we also heard yesterday that there are these attempts to use the Alcock-Paczynski test on the void shapes or on the voids. But that presumes that voids, when you look around them and put them, stack them on top of each other, would form a nice spherical population. That remains to be seen, because they are actually correlated far out with each other. So if you have a certain orientation here, you have more than 100 megaparsecs, still the orientation aligned with that one. So that might be tricky. Nonetheless, people are looking into it. It's a little bit more tricky with, for example, filaments. But one thing is, of course, outstanding. We know that galaxies acquire their angular momentum via tidal torquing. And the same tidal forces turn out to be the agent that are forming these filaments and walls. The anisotropic collapse is a result of tidal forces. So you expect, actually, a relation between the spins of halos and the underlying cosmic web. And indeed, in simulations you do find this. An issue might be that actually the translation towards real galaxies is far less straightforward. So the galaxies are not always feeling exactly the same orientation as their halos, and that sort of murks the underlying sensitivity. But nonetheless, there are indications that there is this relation between the cosmic web and the overall large universe. Then, also with respect to those alignments, then there is the issue, and that is for, in particular, interesting for a lot of astronomers interested in galaxy evolution. They start to recognize now that indeed their formation and evolution is very much sensitive to the cosmic web structure in which they are situated. We know that, of course, already. We know that the clusters are populated by early type galaxies, while the filaments are much more the late type galaxies. But it may go a little bit further. One of our people here present has looked into this systematically, so maybe be able to tell you more about that. Okay. So what I now, having introduced this, what I now want to talk about first is the background of the formation of the cosmic web, and then first introduce, the overall thing of gravitational instability. But within gravitational instability, why do we get these web-like structures? What are they actually manifesting in itself? Now, of course, everything ties in to the formation of structure as it started from the initial conditions. So here is what I find myself always the most very nice rendering of the cosmic microwave background, the WMAP rendering given on two differently oriented spheres. It was a picture made by Max Tegmark, if I'm okay. And what you see here is, of course, the well-known Gaussian distribution of initial fluctuations. That's where we start, right? So how does the cosmic web emerge from this? So very tiny fluctuations, and of course these very tiny fluctuations actually correspond to very tiny variations in the gravitational force field. And the gravitational force field, like what we zoom in over here, you have a slight mountain landscape like this. The slight mountain landscape has valleys, it has ridges, it has mountain peaks, and etc. And of course the mountain peaks and the ridges overall represent regions of higher attraction than those underlens regions where actually effectively the gravity is less than the mean gravity. And as a result, matter starts to displace itself from the underlens regions towards the high density regions, and therefore you get a runaway process, because then of course the situation becomes worse and worse and worse. The higher density regions start to collapse more or attract more and more mass, and in the end they turn around and they start to collapse. So that's the overall background of what we're talking about. I should do something about the batteries of my pointer. So this is the mountain landscape, and then of course we have the density variations with respect to the mean, rho u, and that represents a gravitational perturbation, which we can write as the integral over the density variations weighted by 1 over r squared, but of course over the whole volume, and that in the end leads to the formation of structure like what you see over here. This is of course very simple, but only a couple of points. But what you see over here is, perhaps in the beginning you would say, well, you know, things attract each other and things move out of the underlens region, but you see it's in a particular means. It's not isotropic at all. You see the streaming away from the voids. You clearly see the streaming towards the high density region, but you also see that it's going notoriously anisotropic. It's because the force field is inhomogeneous and actually has higher order moments, quadrupole moments, tidal field components, and they actually induce streams, matter flows, that are themselves anisotropic. And as you sort of get away here, is that you see mass moving out of these structures, first towards flattened regions, like over here, and within these flattened regions, you see them walking towards the overdense regions. And slightly later on, we will see that this is exactly what you expect. So this is a simulation, but theoretically you can see immediately why this would happen. Here, by the way, these images are taken from different directions. So you see real plane from that side, you clearly see the filaments, etc. So the whole story is initial mass distribution, Gaussian mass distribution, represents an inhomogeneous gravitational field that induces an anisotropic, inhomogeneous mass flows towards the high-density regions. That again leads to the build-up of web-like structures. Here there were a couple of more things to see over here, but the low resolution of the beamer may take that away. So that's the overall picture. Nowadays, of course, we have large simulations, computer simulations that show us exactly what is going on, so you can follow it in great detail. So I will show some simulations, and of course that shows that this is what forms. But of course we want to understand more than just look and say, yeah, that's what I expect. Right? We want to understand why. So this is an illustration from the Millennium simulation. This is very shortly at a very high redshift, the distribution, and you see here sort of the first stages of structure formation. You still see an almost Gaussian landscape, not exactly, but you see here the underdense regions, overdense regions, and then you can ask, what's gravity doing in 13.8 billion years? And this is what, this is what gravity then is producing in the same region. So you see the high density node became this outstanding massive cluster over here with this very, very strong filaments sticking out like here, and then a lot of minor tendrils, filaments, sticking out in the filaments connected to the overdense filaments over here, and clearly it's this web-like network. And within this web-like network, you recognize, of course, all the small halos, or here more group mass halos, etc., etc., etc. So this is clearly what you expect from gravitational evolution. So again, a movie does more than just an argument in this way. So this is also a simulation, an early simulation from the Virgo consortium. You see the count from the redshift, it's counting down, and you see how this initial distribution is gradually transforming in the structure that we see in the universe, and clearly you see in red the underdense regions, you see the filamentary structures, you see the way in its connecting, you see the mass migrating via the filaments into the nodes. Let me repeat this again, because a lot of the structure here is the characteristics you can recognize. So we saw the overdense region, but also watch the underdense regions, because they're very nice to see sort of hierarchical build-up. You see a lot of these very small voids, and these are the small voids, and you see they gradually start to merge together into larger and larger voids. It's like a soap sud, right? You have a soap sud in your kitchen sink, and you start with small bubbles, and then after some time you see the small bubbles merging into larger and larger bubbles, and in the end it's only a few large ones, and that's the end of the story. That's what you see here too. So if you look at the downside, the underdense side, it's as interesting as the overdense side. Right? Okay, so when we want to look at the dynamical evolution of the cosmic web and understand it, we should actually therefore pay attention to various factors, aspects of this evolution. I already pointed them out, and I want to touch on at least first three ones. In the next second part of slides, there's a lot about void evolution, but I won't touch upon that. I won't have time to touch upon that here. The aspects I want to look at is the hierarchical formation of structure, the hierarchical build-up of this structure, the anisotropic collapse, why and how, and very importantly, an aspect that does not always figure prominently in studies of this. How do you establish the connectivity between these various structures? Because the connectivity is totally non-trivial. It's what mathematicians call topology. Right? How do you tie all these things together? Because that contains a large part of the story and of the information too. So I will be addressing these kind of things in some detail. So let me first discuss some overall characteristics of the evolution of the filamentary and wall-like distribution of the cosmic web. In the context of an analysis that was based on our MMF nexus analysis, most of it done by Marius in the context of his PhD thesis afterwards. So we were going to look systematically at the filaments. You have to accept from me that this method makes sense, and therefore the filaments and the walls that were actually coming out of this analysis do make sense. We have some arguments for that, but then I should refer you to the papers 2013, 2014, etc. to look up the details of this. I don't want to go into this because of the time. But I will, on the basis of this, given that, want to discuss some of these properties of the cosmic web. Now let me first again look at the movie, and the movie is showing you the distribution of mass in a simulation. We've seen that a lot, but also at the filament population and the wall population, right? So that ties in with it. So if you follow these particles, what would be the evolution of the filamentary and the wall-like web? So here you see the particles going, and in blue you see the filaments, and you really see how more and more the small filaments from the beginning are starting to merge in larger and larger arteries with clearly recognizable nodes over here. Those are becoming the clusters, and they are surrounding the underdense voids. Clearly you see this over here. Here, beautiful node. Here you recognize the filaments, and you see that these filaments actually surround walls. Right? So you clearly see the connections over here. Right? So we are going to follow this in time. Now, one impression, of course, immediate, is that what you see is a configuration of small filaments going towards large filaments. We'll see that filaments will have exactly the same hierarchical evolution as we know of halos. They actually merge into bigger and bigger filaments. They do this in a particular way, and we will see that too. A view of this you can actually get from looking at the surrounding mass distribution around a halo that is living in a wall. And then you see what's going on. So now you're sitting in a halo, and you're looking around you, and you're billions of years ago, and you see on your surroundings this kind of structure. It's already the cosmic web, but clearly you see it's a lot of small filaments. Now you have to keep in mind, this is a view on the sky. So if you see a ring, you're living in a wall, right? Because that's the impression that you would get when you sit in a wall and you look around on the sky, you would see a ring. It's like living in the disk of our galaxy. We see the galaxy as a ring on the sky, right? If you live in a filament, you see two spots. You see one over there and one over there, because you're living right in the middle of a filament. So you see there. So if you watch this, you see what's happening. Here you see it's like you're sitting in minor walls. They're not all uniform. They're very ununiform. But you clearly recognize the structure all over the sky. And as time pursues, here's 4.7, here is redshift 0. You see that these walls start to merge. They form larger walls. You see these things attract towards each other. And here you see the thing is one consistent wall. It's like you were living in small walls that were merging in time together to make a far larger ring like here. In the end, you see that the stuff here in the ring that is in the wall starts to move more and more towards two concentrations on the sky. That's because in the wall you have a filament, a dominating filament, and most of the stuff in the wall is getting attracted towards the filament. And that's the process that you see over here. You end up, in the end, with two spots. It's even more remarkable in the case of this halo. You clearly see a dominant wall over here, but in the end you're left with two spots on the sky. Right? The wall has basically contracted towards a filament. That's the kind of evolution that we see around us. Right? So that's what we are going to analyze. Now, some of these quantitative measures of the cosmic web you see over here. In time, you see that actually, here is at a redshift of around 2, this is a redshift of 0, this is a dark matter simulation lambda CDM, right? So it's not your the complete palette of cosmologies, but it's a rather standard cosmology, so let's see what happens. you see that actually the filamentary network goes down. The length of the filamentary network goes down. That's in line with what we saw in the movie. The tendrils in the beginning were almost filling up a large part of your view, but in the end you saw the huge gaps with some dominant filaments, and that's clearly what you see over here. And it's the same with the surface of the wall network. It becomes less. That's just a manifestation of the hierarchical buildup of the web, in which in the end only the large dominant features remain and all the small stuff has merged into the larger structures. Right? Okay, if you would think that these filaments are uniform, you know, just rods like this, that's not actually what they are. If you would single out a couple of them, and you would actually look, for example, at their density along their line, here is a couple of examples, and you see they rather inhomogeneous structures. That makes sense, because you see these filaments, and in these filaments you see actually minor density enhancements, groups, and minor clusters and things like that. So they are humps over there, and sometimes it's almost like the filament is disappeared in density and then it comes back again, etc. It's just that the density becomes lower, but they are certainly not uniform structures along their extent. Their diameter is also not uniform. Here you see actually a plot of 4 different filaments with their diameter along the extent of the filament. And you see, you know, sometimes they're thick, and then they become thin again, thick, etc., etc. So they are more complex than you would think. Perhaps interesting, we haven't pursued that yet, but it is interesting, given the interest of profiles of halos, etc. You could ask yourself, are there characteristic density profiles of the filaments, or are there characteristic profiles of the walls? Theoretically, you might actually infer this. And here, for example, you see 4 filaments, actually, and you see they do have a kind of a recognizable filamentary or density profile perpendicular to their length, right? So you're looking their density profile perpendicular to them. And you see, you know, it's not bad behavior. You see here you see a very tenuous filament, and you see that here it even dives from slightly overdense, and then it becomes underdense. That's one that is actually sticking into a void, and then, you know, sort of disappears out in the void. And the same you can do with walls. And over there you see, this mean density, that clearly filaments are overdense structures. You clearly see their overdensity here, 10, 100. Right? So this is a massive dominant guy. This is an underdense guy. But if you look at the walls, the story is quite different. A lot of them are actually mostly underdense. Actually, you can forward analytical reason why walls prefer the void-like regions and the filaments prefer the overdense regions. You can get it actually from Gaussian field statistics, as was pointed out by Gaussian in 1998, I think, or something like that. And this is exactly conformed to what you see over here. So the walls are more towards the lower density regions, the filaments more towards the higher density regions. Of course, the physical reason is that to form a filament, you have to pursue further into the evolution, the dynamical evolution of such a structure. So it should have assembled more mass, it's in a more advanced stage, and that's in the overdense regions, while in the underdense regions, everything goes slower. So it sticks to the sort of the wall-like configuration. Other evolutionary trends. You could, for example, say, okay, filaments, what happens to the mass content of the filaments, right? Now, or to the walls. Actually, they're not always composed of the same matter. Matter is streaming in the cosmic web. That's actually where a lot of interesting work has been done in the past years to see, you know, the streaming on large scales. What you actually see is that part of the mass passes from the voids, and if you remember the simulations, you clearly saw mass streaming out of the voids towards the high density regions. Most of the stuff goes subsequently from the walls into the filaments, and along the filaments, which are sort of the highways of the universe, they are streaming towards the nodes. That's the overall story. But for example, you can investigate this, and this is a couple of plots. For example, here you see you can actually recognize what's happening to the various components. And for example, you see that a lot of the underdense, this is the that originally at the redshift of 2, and this is moving towards the filaments. All of the stuff in the walls is actually towards the filaments, and you can sort of characterize things like that. You can actually also see what's happening to the stuff in the filaments. Where is it moving towards to? So most of the filament stuff is going towards the clusters, most of the walls is going towards the filaments, etc., etc., etc. You can even do it particle by particle. For example, here is the cosmic web at the redshift of 2. And here you see all the particles that at the redshift of 2 were recognized as filaments. When they are red, those guys, in the end, at the redshift of 0, have ended up in cluster nodes. The guys who are blue have remained in filaments. The guys who are green actually moved out of the filaments in the walls. Turns out that this sometimes happens in the boundary regions too. But at the same time, you can ask yourself, a filament at the redshift of 0, like here, where are you coming from? You see it's dominated by green points. The green points at the redshift of 2 were in walls. So most of the filamentary material that at the redshift of 2 was in the walls has ended up in filaments at the current epoch. And you can play the same game for nodes and etc. You can ask yourself, where did all the stuff in voids come from that nowadays is in the voids? And you see that nearly everything is black, with a few exceptions, blue and green, but most of the stuff that nowadays you would recognize as voids actually always was there. Some of the stuff, like what you see here in blue, you would say, how's that filament that goes into a void? Actually what's happening is these bubbles. They're merging. So you remember these small bubbles? They were building up. Now at the boundary of these small bubbles, there is still material that you recognize at the redshift of 2, like a small filament. But now at the redshift of 0, it has merged in a larger void, and there's still stuff streaming out, but because it's underdense, it goes very slow, right? And so you say, this guy at the redshift of 2 was in a filament, but it was a tenuous one, right? So overall, you see this here. And so you can play the game, the migration flows in the cosmic web, like this. You could even look at the mass functions of filaments. So you could single out single filaments, and you could ask yourself, what's happening? And here you see, going from redshift of 2, and this is the mass that is in the filament, how is my mass function evolving? And you clearly see the shift towards higher masses. So you clearly see the shift from small to large-scale filaments, exactly like what you see in a hierarchical distribution. So it's really a nice reflection of hierarchical evolution of the cosmic web, of the filaments. Let me skip this one because I thought. Yeah, this is another one. Here is the shift in diameter evolution. So here you see a redshift of 2 that goes to a redshift of 0, and this is the filament distribution. And you clearly see that the filaments in time become thicker, exactly confirming what you saw in that movie. The same thing happens with the wall thickness, but it is you know, so here you see how it is. So you see here the shift towards thicker and denser walls. But also look here at the small side of the walls that are more tenuous. They actually become less thick because they're disappearing. Right? So the story for the walls is slightly different than the ones for the filaments. Observing astronomers would want to know, well, that's nice, but this is all dark matter stuff, I cannot see this, so this is all academic exercise. But you can, of course, also ask, what then about the population of objects in those filaments? Halos and, connected to them, the galaxies. Also there, you see some interesting artifacts. You could, for example, identify the halos and look at the halos in the clusters and in the filaments and in the voids. Now, this is the halo distribution in nodes. You recognize that it's very high dense objects. This thing here is just an artifact of the fact that, of course, in the nodes it's very hard to identify the objects and you should have sub-halo identification, etc. That's not as convincing in that sense. But look at the filaments. The filaments clearly have far more massive halos than the walls and than the voids over here. The voids, according to this picture, are populated by very minor objects. And actually, when we looked in the Sloan Digital Sky Survey, identified voids, looked for galaxies that perhaps were still living in there, and then we observed them in H1, and we observed them in infrared, and to optical bands, etc. It turned out that nearly all of them, with the exception of two, were tenuous blue blobs with masses of less than 10 to the 9 solar masses. So the voids really are populated only by the minor objects. But the same thing holds true for the walls. Now, what's the consequence for this? The mass function of halos living in the walls is clearly towards lower mass objects. Now, try to imagine yourself doing a survey, a magnitude-limited survey like Sloan, Bos, etc. Of course, you have a very heavy cut in mass. And usually it's pretty high. And as soon as you go out of the immediate realm of our galaxy, you can't see them anymore. So walls have two real downsides. First of all, their surface density is very low. That already, in such a simulation of dark matter, makes them hard to find. You can, theoretically. But then you translate this into the mass distribution of the halos, and you find it's only minor objects that I cannot see in my magnitude-limited survey. No wonder that when you look at these surveys, you hardly see these walls. It's simply almost impossible to see them. Here you see them. This is a wall, and you see in blue, that's only the minor halos. While you see a filament over here, it's populated by all these heavy guys over here. Right? So it's a sort of a feedback process. You don't have enough mass to form heavy objects. That means you can't see them. And it's a real systematic thing. You could look at the various populations like this. So we did that. Look at the filament like this, and then look at the different masses, density in those things, and then compare that to the halos, and you see these are very massive halos, and you have the very tenuous ones over there. So you can systematically investigate all these properties. You can actually also look at the evolution of the halo population. So, for example, you can see that overall, actually the mass of those objects in the voids and the walls is growing. So the mass function of the halos is actually becoming more massive. That's also result of the hierarchical process. So you could even look, for example, and compare between a redshift of 2 and a redshift of 0, and what the various mass, where the various mass objects are. So you see, for example, all the massive halos are just in nodes. And if you have a 10 to the 12 solar mass halo, or 10 to the 11, well, 10 to the 12 is more thing. You see every one of them are in filaments. But if you then look at 10 to the 11, so galaxy size, you see most of them are filaments, but a sizable fraction could be found in walls. In that sense, at that mass, it's not that much different from a redshift of 2, but at the higher mass end, it certainly is. Okay. I'll see 30 more minutes. In hindsight, I'm grateful, Paco, that you gave me this time. So now about the dynamics of the formation of the cosmic web. So we discussed the general properties that we sort of see, you know, set sort of the scene of the filaments, walls, migration from one end to the other one. Where does it all come from? It all comes from anisotropic collapse. So we all know about gravitational instability. That's a clear characteristic of structure formation. Overdense regions overall represent regions of higher gravitational interaction, therefore matter moves up to them, assemble more mass, more attraction, assemble more mass, and collapse. But there's a second very important characteristic of gravitational collapse. That is intrinsically, it's anisotropic for the same reason. The anisotropy is an instability. That was pointed out, or that was realized for the first time by Zeldovich, and later on I will pass a more general argument. So I always like to show this picture of Zeldovich because it figures so predominantly in this field. If anything, I said in 1986, de Labra, for the first time saw a cosmic web-like structure. And should be fair, actually, in the 1970s there were people like Jan and Nasto who had already pointed this out. Jan would be very angry with me if I had not pointed it out. Observationally, there were hits, but in 1970 there were none, observationally yet. But this guy, Zeldovich, realized it from, at hindsight, rather direct, straightforward physical arguments. Zeldovich developed a formalism, a simple fluid dynamics formalism, which immediately showed that from a given primordial distribution of mass, you would form anisotropic structures. I always like to show this picture because I had a couple of Russian friends who told me hours and hours of anecdotes about Zeldovich, and you know I always like to show these. For the younger generation, most of the people here are young generation, these are medals of hero of the Soviet Union. 3 times. So you all know Zeldovich as great cosmologist, right? Well, this one was for the Stalin organs, the Kamchutkas, you know, the little missiles that the Russians used in the Second World War. He solved the problem of the solid propellant, because up at the time these little rockets came up and went down on the soldiers who shot them up, so that was not very healthy. He solved the problem, and he was a chemical engineer. And so he solved the critical problem, and that's why Stalin thought that he should get his first order. More scary is this one. It's the first Russian atomic bomb. He built it with Sakharov. And this is the Russian hydrogen bomb. He built it with Sakharov. So this guy is really something. If you want to know about shock waves, the standard book on shock waves is from him. You can still buy it. And then think, that's nice, if I study supernovae, I have to know about shock waves. But you should realize it's all been experimentally verified. Right? So this guy had these medals for this, and after that he was allowed to do irrelevant stuff like cosmology. So, but you know, the guy for our field is a hero. Absolutely. I can tell some more stories about those medals, but in particular for students. What he showed is that when you look at the evolution of mass to a first order level in Lagrangian space, that is just looking at mass elements and how they displace themselves in space. It's very simple. You take the initial location, and what then turns out is that to first order Lagrangian perturbation, we heard about 2LPT, but this is the first order that provides you young, is a simple uniform factor dt times a velocity u. And the velocity u is actually the gradient of the velocity potential, and actually for the gravitational perturbations, this velocity potential is directly proportional to the gravitational perturbation in one go. And it's all as a function of q, that's the initial distribution. So, the initial distribution is your Gaussian primordial field. You calculate the density distribution, some realization. You simply, from that, get the velocity potential. From that, you get this velocity, and it's the velocity in the initial, according to the initial phase. So you don't have to do anything more than that one instant. And subsequently, what you get is a ballistic motion like this. Now, the issue is that this thing makes a mass element move from here to here in a ballistic motion. But the interesting thing for pattern formation is to look how it differs as a function of the initial location. So then you see, how much does my neighbor, where does my neighbor go? Right? And then you see, oh, my neighbor is also listening to the gravitational gradient, or to the gradient of the gravity, or of the velocity potential. But it may differ a little bit if there is a second order, or the second order gradient, the Hessian. That is the tidal field. So if there is a tidal field, and actually in a Gaussian distribution there is, you actually get a difference in displacement between the neighbors. And that means that the original distribution is actually deformed in one that is different. So how does it look like? Well, let's have a look. And it's totally simple. Right? You can do this on your cell phone, at least if you're a good programmer. So this is what you get. This is a Gaussian field. It's simple ballistic motion. And what you get is actually a displacement of mass from the original position. Now this is, of course, overcooked. This is nowadays, and it clearly is going wrong somewhere. But the initial, look at it, it's how this is the cosmic web. And he realized it in the years later, that actually matter should have assembled in a cellular kind of distribution as it was described in those days. This was the Soviet school of cosmology. In the West there was a completely different school. The very nice thing is that this is a top-down view of structure formation. And of course the West had the bottom-up. So the political views of the different systems was actually reflected in their cosmologies. Right? And it was the Estonian group that then came up with observational evidence that something like this had formed. So this is precisely because of what is a gradient in basically a tidal field. The second order gradient of the potential field must form structures like this. Right? You see filaments, you see walls, you see nodes. One warning, you clearly see it's overcooked. We will get back to that. The reason is there is no stopping. Once you move out of this thing and end up here in a structure, gravity would tell you, like, hey, density went up, gravity becomes stronger, pull back. But this guy is not pulled back, it goes on. That's why you get these artificial structures like this. We will see that soon that the Soviets also solved this problem. Now, all this material, and that's what I hope to end with today, is actually very beautifully described mathematically by a theory called Catastrophe Theory. That's where I want to end up today. It's something that all of you recognize. If you, for example, go to a nice harbor in the summer with yachts, and you see the undulating water, and when it's bright sun, you see patterns on the sides of the boats, like this. It's exactly the same thing. It's basically light propagation through a plate of glass here, or in the case of water, it's the surface of the water. And it causes the same patterns. Mathematically, it's the same thing. We will see that the cosmic web has very much to do with this. Now, why would the Zeldovich approximation actually suggest then this anisotropic evolution? Here comes another important observation. When you take this thing, then you actually could look at the density distribution, and the density distribution implied by this, of course, follows from the Jacobian of this displacement field. That is, this thing comes in. So actually, when you do your maths, you see that you end up with the gradient of this velocity, and that is the deformation tensor dij, and you can actually take the eigenvalues of this thing and end up with a very nice expression, overall density divided by 3 factors. Each of the factors, the eigenvalues of this deformation tensor times this growth factor. And of course, what you get is when one of these factors turns to 0, that is when d times lambda is 1, that is at the time that lambda becomes 1 over d, or d is 1 over lambda, then you get collapse, because the density goes to infinity. So the prediction is collapse along one axis. Slightly later on, you go along the second axis. Hey, this will be happening to all my guys in the neighborhoods. This will be a wall. Then you go to the second one. That's all the guys in the neighborhood go along 2 directions. That's a filament. When you're lucky, and this thing is also larger than 0, need not be, then this thing even can go to 0 and you can get a halo. All 1970. And it was all there in explanation, right? Of course, it's only at hindsight, now we have the richness of the observations and simulations, that we see how incredibly good this was. At the time, it was even thought that this was only the first stages of evolution. It was when we got the simulations that we realized that this approximation was almost holding up to the moment that filaments and walls were forming, that it was damn good. To a certain extent, it was lucky in that sense, but that's why Zeldovich is still a predominant name in the field. He basically laid out the framework. Later on, Bridget is going to talk about phase space evolution and matter streams, because of course what you get in the formation of these structures is you get these collapse structures. But that of course ties in with velocity streams coming from different directions. And here you see where a catastrophe starts to happen. When matter is coming from this direction and matter is coming from that direction, there is something fishy going on, because all of a sudden the X, one particular location, is no longer tied into one cube, but two different ones, or 3, or 4, or 5. You know, matter streams coming from different directions. And it's actually that over the past I would say since 2011, 2012, a range of studies have come forward where actually people started to look exactly in the interest of these multi-stream regions, because a lot of understanding is hidden in that multi-stream aspect. Up to that point, it was sort of discarded. So, how does all of this tie in together? Cosmic web connectivity. One aspect that I certainly should mention is, how does all this stuff then tie together? This is the next stage in the cosmic web story, I would say the next after. It goes back to a realization by Dick Bond and then Hoffman and Dmitry Gaussian that actually coined the word of cosmic web. Before that, it wasn't called like that. In all, it goes back to the following. And this is gravitational instability number 2. If you collapse a certain mass, like here, spherical objects in the primordial universe do not exist. They have probability 0. So any structure that you have will have a slight, even slight deviation from sphericity. What will be the result? Just single out the object. Don't think about the forces coming from the outside. It means that the gravitational acceleration along the small axis will be slightly larger than along the long axis. Just think about it. Draw a circle here, and you see that the gravitational attraction from that inside encompasses the complete overdensity of the ellipsoid. Right? So that's this. Then draw a circle on the outside, like this. Then it's a mix of the interior and the exterior. So that's a smaller gravity. That means it will start falling faster along the short direction than the long direction. And then, of course, in the next time, it's even more outstanding. So you get actually an acceleration of collapse along the short axis, while the second axis remains behind, and the third one remains to be seen. This is an instability. This is also gravitational instability, but it's the instability for actually the formation of anisotropic structures. This thing is actually full nonlinear collapse, and basically full nonlinear anisotropic collapse. Now, how in reality this is actually augmented by the fact that this force field, which is actually a tidal force field, that is, there is a difference between this side and that side, on top of that is the inhomogeneous distribution from the outside. So the inhomogeneous from the outside, you can actually take into account what then is the gravitational force field that is coming out of a certain density distribution. And you can actually write down, like for the gravitational acceleration, the expression is an integral over the density distribution times the quadrupolar component. Right? So that's actually what's driving the anisotropic collapse. Now, if you have given a certain configuration of the tidal force field that is forming a filament, how would it look like? Well, I would say that there would be collapse along this axis, and there would be collapse along that axis, and there would be a stretching along that axis. Could I actually turn this around in an inversion where I take this configuration and ask myself what's a typical density distribution that is causing this collapse? Right? Let's do it. There's a technique for it, constrained fields. I think Jenny is going to talk about that, right? So you can actually talk about this and ask yourself, what is happening if I have typical filaments like over here? You see the bars, they are the tidal bars. And you ask yourself, what's a typical configuration? What you get is a typical quadrupolar mass configuration And that's two nodes over here with some minor stuff in between. So what you actually get, typically, is here is a filament going to form, and on the sides of the filaments, you get two overdensities, clusters. Remember that we were talking about clusters with filaments in between? Here it is. It's implied. It's actually a result of the fact that if you want to form a filament, you should have major mass concentrations around you that make it collapse along two axes. That's where the weaving of the cosmic web comes in. And here you see actually the tidal force field, and you really recognize, for example, these are the filaments, and then here you see all these high nodes of the cosmic web. Now this is actually what made Dick Bond and Les Hoffman and Dmitry Gaussian in 1996 realized that actually the cluster distribution is intimately tied in to the filament distribution. And they showed this on the basis of a constrained field formalism. What they did is they took a mass distribution, they identified 5 of the heaviest peaks, then they did 10, then they did 20, and each time they calculated what the implied Seldovich configuration would be. And you see that as you descend down the mass distribution, you get a more and more accurate filamentary and wall-like web. So this establishes the links between the nodes, the filaments, and the walls in the whole story. You can even, on the basis of that, say, well, that's coming from my initial Gaussian field. So if I take these signatures into account, collapse, collapse, stretch, or only collapse and stretch, stretch, where are they? Right? You just take the gradients of your force field, and you can actually, for a Gaussian field, do the statistics. Dmitry Gaussian did this, and he pointed out that sheets and walls are living actually in underdense regions, mostly, and filaments in the overdense regions. That's what you sort of get. And this is a pretty straightforward statistical argument that you can follow up. In view of the time, I'm going to skip this thing. That's the adhesion model of the Russians. Well, no, shortly I should discuss it shortly because I want to go to the singularities and the caustics. Maybe I should. Fine. Yeah. So, but it's too nice. It's wrapping. It's literally wrapping up the talk. So, Seldovich. Now, Seldovich had a problem. Seldovich did not take into account self-gravity. So here you see the flow of mass through the universe, implied by the initial mass distribution. Where does it go wrong? Why doesn't he stop in the overdense regions? The reason is because if you look at the Euler equation corresponding to the Seldovich approximation, and you rewrite it in a proper way, you actually see that you get a source-free Euler equation. In other words, this is ballistic motion. There's no gravity in it. That is, if you compensate for the overall initial gravity, 0. But that should not be, because the structures they're building up should represent gravity. Now, the only thing you can do is either you take perturbation analysis to the next level, or you, and that's what people now are doing quite successfully, but at the time they did not, or take simulations, do the full nonlinear distribution. But what do you do if you don't have massive supercomputers around? And this is one of the nice stories, I think, of the Soviet cosmologists. They didn't have. So they thought of something else. See how they actually introduced an artificial term on the right-hand side, which has nothing to do with gravity, but it's a modeling of gravity. It's a viscosity term here, so it's a sticky term, right? So you just plunge it over there, and it sort of models your gravity. Now, why this particular way? that came from a plasma physicist who said, well, if you take this equation, that's an equation that we in fluid dynamicists know very well. It's Berger's equation. And you can solve this thing completely analytically. So actually you can incorporate a sort of a model of gravity by putting this term in and evolve it further on. Now, let me pass on the details, but Johan Hidding, my student, solved this in a beautiful geometric way, in which he was able, in a full three-dimensional distribution, to solve this very rapidly. He had to solve for this equation. So you actually have a Q, and with the Q you want to find an X, right? You see, this is not the original Zeldovich distribution. This is the Hopf solution, it's called, mathematically. And it all comes down to actually solving the convex hulls of the potential. Forget about it, it's geometry. So you can do this, and you actually can get a beautiful model of the hierarchical buildup of structure in the universe. You actually see the filaments merging with each other because they stick, as they show over here. Now, this thing, I won't go into the details, but I will show you this movie, which is exactly the same distribution as the Zeldovich one you saw, but there is no problems. You see a beautiful hierarchical buildup of the structures. You see the small voids merging, you see the small, you get actually the hierarchical evolution of structure in the universe. Right? This is, if you see the papers from Shandarin and Kaufman from around the 1990s, can I have 5 more minutes? Then actually you see they already managed to do this. This they forwarded in 1989, and you know that a year later the Soviet Union collapsed. I don't think there was a causal connection over there. I would rather say this is the last major contribution from the Soviet Union to cosmology. Right? So, now I'm very fast going to the last part because I'm very okay. It's this thing, and Richard Falk will tell more about it. It's about the formation of structure in phase space. So what this is all about is not talking only about the fact that you can look at the streams of matter just in space, but you actually do full phase space. So you have velocity versus space. And here you see what's happening. The uniform distribution at 0 is gradually getting deformed. Here it's still that you see one stream, but here you see actually the formation of a wall, and you see what's happening. It's wrapping around. You get multi-stream regions. And these multi-stream regions now have a lot of interest because they actually should tell us what's happening in the cosmic web. They even should tell us where the filaments are. They're 5-stream regions. Where the walls are 3-stream regions. They are those. So there's been a lot of activity in this. So you get, for example, in phase space, a wrapping like this. And when you would look in detail at the density structure, you get these peaky distributions. The peaks happen here. They're called catastrophes. Because over there, one X corresponds to a whole range of Qs. The proper view is this. This was an image made by, again, by Johan. And this is the way you should look like. The blue is the dark matter sheet. So it's in phase space. And as you evolve, the red one is what you see in space. So you see the distribution of mass in the universe is like a 3-dimensional sheet in 6-dimensional space being wrapped. Right? That wrapping is mighty interesting, mathematically speaking. I'm going to skip this thing. It leads to very high resolution of the density field. But what I really want to show is recent work, what we did. Now, Why is this wrapping interesting? It's interesting because it allows a lot of the dynamics, but it's also beautiful mathematics. Some colleagues of mine always insult me in saying that I'm a mathematician and not an astronomer, but it is too beautiful. Now, Job Veldberg is one of my students, and he's very, very good mathematician. So what he did is he looked at what's happening to these wrappings. He focused on the wrappings. So what you get is the following. You, for example, look at a certain distribution, and for example here you see a mapping from the initial position to the final position. Now what is this dictated about? Remember this expression from Zeldovich with the different eigenvalues. But the eigenvalues are actually determined by the initial Gaussian field. And it varies. So we haven't looked in detail at the specific spatial properties of this. But remember, if you look here at the contours, these are the contours of the lambda 1. Right? So what's happening to this thing? This ring in the initial distribution is precisely the points where lambda is equal to 1 over the growth factor. These guys are collapsing. So when you look at these things and look then in the Eulerian space, that's what you see in the nonlinear space, you see what's actually happening. This stuff gets wrapped into a plane, and at the tips, you actually have tips like, you take a sheet and you fold it like that. And these are called A3 caustics, because you wrap it like this. And you can continue this story, and go on and on and on, and actually take your field and identify in lines everywhere where different wrappings happen. And remember this movie of the wrappings of the phase-space sheet. So what Job did is they identified in a context, because this is what we did into the past 2 weeks. So it's okay, thank you very much.